Hi there, my name is Raymond Doe, and welcome to my Physics 2211 Lab 2 Motion of a Falling Object experiment video. Hope you enjoy. In this lab, we will examine three different position over time motion models of an object falling from rest with the purpose of observing the properties of Newton's second law of motion and the effects of the forces of gravity and drag acting on said object in free fall. Using tracker software and two computational models via GlowScript, one accounting for the drag force and the other negating it, we are able to determine not only how accurately the computational models reflect the observed motion, but also predict the final position of the falling object. By the end of the lab video, we will be able to understand the physics associated with net force and the motion of a falling object. We will also observe and comprehend the interconnected effects of gravity and drag on the predicted velocity and position of said object. Three key concepts we'll be exploring in this experiment includes Newton's second law, which states that the net force of an object is proportional to its mass times acceleration. In this case, g will be substituted for a, as it is the acceleration due to gravity. We'll also be taking a look at the force of gravity and weight, F of g, which can be computed as negative the mass of the object times the gravitational constant, in this case 9.8, times the unit vector of the object's coordinate system. We'll also be taking a look at the drag force, which is the force that acts opposite to that of gravity. This force pushes up on a falling object while gravity forces it down. Firstly, let's examine our tracker data, which we can use to generate an observed model of the object's falling motion. As you can see on my screen, I've clearly labeled the system, with my object being a Christmas ornament and my surroundings to that system being drag and a force of gravity. If you look to the right of your screen, you can see a plotted observed model of the object's position, and below it numerical values of time and position. These values we can use to plug into our GlowScript computational code to generate a predicted model, including gravity and accounting for drag as well. Moving over to our GlowScript computational code, we'll first generate a model accounting for gravity only. We set up our initial conditions with the mass of my object being 0.283 kilograms, the initial position being 0, and the initial velocity also being 0. For my while loop, I said while time is less than 0.544 seconds because that's the last recorded time from GlowScript. And as you can see below that, I have the weight formula that we spoke of before written out in a computational code form. The net force for this model will only include the weight of the object and not account for drag. Below this, you can also see the position and velocity update formulas embedded into our code. Our second computational code that accounts for drag as well as gravity is very similar to our first, with only notable differences being the inclusion of a proportionality constant on the left and the inclusion of a drag force being added to the weight in our net force equation on the right. This is our resulting graph plotting all three models of our falling object, including the observed tracker data in both GlowScript codes, accounting for gravity with and without drag. As you can see, the model exhibiting the steepest slope is formed by the motion of the object falling due to gravity without drag, while the observed motion and the model accounting for gravity and drag have flatter slopes. This indicates that when considering drag, the object will fall much slower than predicted than when simply considering gravity. This is because, as mentioned before, drag force acts the opposite of gravity, thus pushing the object up while gravity pulls the object down. You may also note that while the observed motion more or less reflects the gravity with drag model, it is not completely identical. The differences between these two slopes could be due to mass discrepancies in the code, inconsistencies in the surrounding air conditions of the room in which my object was dropped, or slight miscalculations in the proportionality constant. When asked if either of my computational models can predict terminal velocity, it's easy to see that my second model that accounts for gravity with drag will be the one to do so. And as you can see from the velocity and time graph shown before you, the change in velocity of the second model will slowly and eventually decrease to zero, displaying the equilibrium, while the velocity of the second graph is constant and is showing no signs of stopping. This is because there is no drag to counteract that gravitational acceleration. Changing the initial velocity of the object's descent would not change the motion's terminal velocity. This is due to the nature of terminal velocity being solely dependent on the amount of drag counteracting the acceleration of gravity, which would not be influenced by the object being thrown. Thank you for your attention, and I hope you have enjoyed.